In this video, we're going to look at inverse functions. We're going to use compositions of functions to verify that we actually have two functions that are inverses of each other. We're going to determine the domain and range of inverse functions, restrict the domain where it's appropriate to make it one-to-one so it will have an inverse. We're going to find and evaluate the inverse of functions, and then we're going to use the graph of one-to-one functions to graph its inverse on the same axes. So we're going to start with a warm-up of the composition. Previous video, we just did composition, so this should be nice and easy reminder. So there should be an F right there. So F composed of G of X is the same thing as F of G of X, which is F of X minus 3. So I put in X minus 3 into this function wherever I see X. And so I get X minus 3 plus 3, which gives me X. G composed of F of X is G of F of X, which is G of X plus 3, which is equal to X plus 3 minus 3, which also equals X. Now let's take a look at the next one. So I'm going to do F of G of X, which is F of 2 minus 3x, which gives me 2 minus 3x, the quantity squared, minus 2 minus 3x, and then plus 1. And I'd let you simplify that. So then the composition the other way, G of F of X is G of x squared minus 2x plus 1, which is equal to 2, x squared minus 2x plus 1. And then that's not right. It is going to be 2 minus 3 multiplied by x squared minus 2x plus 1. I was getting ahead of myself and I don't know what I was doing. So there, I would let you go ahead and simplify that. That is not the final answer. That is just how we're going to approach it. And I'll let you all find the final answer. And of course, we will go over these in class if you would like. Now we're going to do the next one, F of G of X, my next example here. And so we have F of the square root of X plus 3, which is equal to the square root of X plus 3, the quantity squared, minus 3, which gives me X plus 3 minus 3, which gives me X. Now composing it the other way, G of F of X is going to be G of X squared minus 3, which is going to give me the square root of X squared minus 3 plus 3, which is going to give me the square root of X squared, which is equal to X. Last one, composition, F of G of X, which is F of 1 over X plus 1, which is 1 minus 1 over X plus 1 over 1 over X plus 1, because everywhere I see this lovely X, I'm going to replace the entire thing with 1 over 1 plus X. Now this one I am going to help you simplify. I'm going to go ahead and multiply the numerator and denominator by X plus 1 so that I can clear my fractions. This gives me X plus 1 minus 1 over 1, which gives me X. The G of F of X is G of 1 minus X over X, which is 1 over, I'm going to replace this X with 1 minus X, so 1 minus X over X plus 1. I'm going to multiply the numerator by X and the denominator by X. That'll clear my nested or complex fraction. This gives me X in the numerator, and then in the denominator, I'm going to get 1 minus X plus 1, which gives me X over 2 minus X. Nice, easy, just refresher of compositions. So now we're going to define what one-to-one is, and we actually seen one-to-one in functions, and we didn't spend a great deal of time on it, and I said we're going to do this later. So now we're going to really delve into what a one-to-one function. What a one-to-one function is, it's a function. So for every y, there can only be one x, or for every x can only be one y associated to it. And then one-to-one adds another layer. A one-to-one function is a function in which for every x there's only one y, and for every y there's only one x. So not only does it have to pass the vertical line test to make it a function, it now has to pass the horizontal line test to say that it is a one-to-one function. If you are given a graph and you're trying to determine whether or not it's one-to-one, drop a vertical line anywhere on there and a horizontal line anywhere on there. And if it only touches the graph once, regardless of where you put those vertical and horizontal lines, then it is a one-to-one function. Sometimes your functions are not one-to-one and you want to find the inverse. So you need to restrict the domain appropriately so that it will produce every single possible output value. So if I take a look at my first example and they're asking me to restrict the domain. If I restrict the domain, say at 2, I want the domain for this function to be greater than 2, I would get all of these output values. But you'll notice I'm missing these output values. These output values on the left side and right side would be the same output values, but I'm missing a whole bunch of output values right along here, right? So this whole area, I'm missing my output values. So I'm not going to restrict my domain right there. I'm going to restrict my domain in which I have all the possible output values, and I'm going to restrict it in such a way that it is one-to-one. If I restricted my domain right here, say I want to have my domain so it is -1 to infinity, then here we go. Here's my -1 to infinity. Here's what I'm going to get. So I get all my possible output values. But in this region, you can see that I'm not going to pass the horizontal line test. So I'm going to restrict my domain right here. So the domain I'm going to restrict this to, so suppose this is f of x. My domain of f of x, I'm going to restrict it so that I start at 0 and go to infinity. Or I can have my domain of f of x to ensure it's one-to-one to go from -infinity to 0. And that is a terrible infinity. That is a negative infinity. That's terrible. So one or the other, but not both. Same thing with this absolute value. Now suppose this is g of x. I can either restrict my domain so I have this side of my V shape getting every possible output value. So I can say I have the domain of g of x could start at 2 to infinity, or I could have my domain of g of x to be such that it is -infinity to 2. Just depends on what is the most appropriate. I usually choose the positive side. If I'm not required to choose one or the other in particular, I'll choose probably the positive side. As I take a look at this function and I'm trying to decide what is going to get all my possible output values. Again, if I restricted it right here and I say I want all of these, this part of the graph is not going to pass the vertical line test. So if I restricted it right here, then you can see I'm missing all of these possible output values. So once again, I can choose the left side or the right side, and I'm going to either go on this side or I'm going to choose this side. So suppose this is h of x. My domain of h of x, I'm either going to have it be from 0 to infinity, or I'm going to go from -infinity to 0. Now, before you're like, wait a minute, don't you have a vertical asymptote? And the answer is yes. Okay, so let's talk about that vertical asymptote. Typically, we would wait until rational functions, but you can see I have this vertical asymptote, which means I really have to talk about I can't have that value, and that value happens to be 2. So it goes from 0 to 2, and then from 2 to infinity, or from -infinity to -2, and then -2 to 0. So either one of those would work. That's just because we are going to talk about rational functions. They are going to be coming up, and wherever I see these vertical lines, those are the restricted domains, which means they're vertical asymptotes, which means I have to really kind of say I don't get to actually have those anyways. Take a breath. Put me on pause, go get something to drink. Now we're going to talk about inverse functions and compositions. this is how we're going to define what an inverse function is and how we can check it at the same time. Suppose f is both a function and one-to-one. Then f inverse, that is not the reciprocal, that is not 1 over f, that is f inverse. So f raised to the negative 1 means f inverse. We'll hold that the composition of f composed with its inverse of x is equal to x for every x in the domain of my inner function. So this is where composition comes into place. And composed the other way, f inverse composed with f of x is equal to x for every domain of my inner function. In this case happens to be f of x. If this holds true, then I have a one-to-one, or I have an inverse, and those inverse functions are both functions and one-to-one. So how do we do the inverse function? If I'm asked to just determine it, I'm going to put one inside the other. If I put one inside the other and I get x for every value within the domain of the inner function, then it is those two functions are inverses. If it's not, then it's not. So let's take a look at our first example that we did. We did this and we said f composed of g of x is equal to x, and we did g composed of f of x is equal to x. And we said when we did that, the domain of my inner function in this case and the domain of this inner function are both real numbers because of the fact they're linear. Because they both equaled x, just strictly x, then these are inverses of each other. So we say this is true. Now with b, we didn't actually simplify b, but if you were to simplify b, you would find out that these are a no. They are not equal to each other. On c, you would be inclined to say, wait a minute, I came up with x in both ways. Well, yes and no. So, f composed of g of x was equal to x, but the domain of my inner function was negative 3 to infinity. So I couldn't even put anything into my inner function on the left side of negative 3. Since I can't put anything on the left side of negative 3 to get x, so if I put a negative 4, negative g of negative 4 is not going to give me negative 4. So even though I had g composed of f of x was equal to x, even though we found these to be equivalent, it failed because of my inner domain. I can't put, to begin with, I can't put in negative 4. So there are places in which my domain values are not going to equal itself. So what does that mean? This is one of those cases in which I'd restrict my domain. This is going to be true on this restricted domain. So I could say, oh, these are inverses of each other, provided, of course, that x is greater than or equal to negative 3. And on our last example, we did not get them to be equal to each other, so we know that this one is a no. So I have two, actually I have only one yes and one that's sort of if I restrict the domain, yeah, okay, it works out. Because I'm doing the domain of one becomes the range of the other, and the range of the other becomes the domain of the first one, domains become ranges and ranges become domains. And I had a student years ago and something about a ranch and cows, and I don't remember what it was, but it was funny then and I should have paid attention, but I just don't remember, so I can't tell you about it. But if you are my student, I had years ago about the cows and the range, and I was in Colorado at the time, and I was thinking, well, that's appropriate for Colorado, but not really so appropriate when you're, outside of a bigger city in Washington State. So, okay, if you are that, throw that in the comments. I'd like to remember what that was. Something about domains and ranges and inverse functions. Okay, because domains become ranges and ranges become domains, then this has to hold true. The graph of one function can be graphed as the inverse if I reflect it over the line y is equal to x. So if this point is on the original function, negative 2, 0, then the inverse would be 0, negative 2, because domains become ranges, ranges become domains. So suppose my function had this as the domain of g, and this time I actually get to use just single points. My domain was -2, -1, and 2. The range of G was 0, 3, and 4. Then this becomes the range of G inverse, and this becomes the domain of G inverse. Domains become ranges, ranges become domains, and they will be reflected over the line y equals x. So how do we find the inverse of a function? Well, first of all, we want to make sure it's 1-to-1. Why? Because if it's not 1-to-1, then it's not going to pass the inverse. When I try to do the inverse, and reflect the graph over the line y equals x, is not going to be a function. What do I mean by that? Well, okay. So suppose I've got this. Y is equal to x squared, and this is my function f of x. If I tried to graph this over the line y is equal to x, then my inverse function would look like this. This would be f inverse of x. But if I try to drop a vertical line on that, you can see that it's not going to be a function. Therefore, it has to be 1-to-1 to begin with. If it's not 1-to-1, we restrict the domain to determine what would be the best choice to restrict the domain. Then I'm going to replace f of x with y. I'm going to solve for x. When I get done, I'm going to have x is equal to, I replace f of x with f inverse. I replace y within the equation f inverse of x is equal to x. So I'm only in one variable, and I check the composition both ways. This is one of those times in which you will always know whether or not you have the inverses because you do the composition. If they are not the same, either you made a mistake on your inverses or you made a mistake on your algebra when you're checking the composition. This is really nice to always know whether or not you're always right or not. I mean, there's no guessing. You're either right or you're not based on your composition. Unless, of course, you made a mistake on the composition and you made a mistake on finding your inverse, and then, well, then it's wrong. A lot of wrong. Okay. What does step 5 do? Step 5 is the moment that our domains become ranges, our ranges become domains. And do we have more than one inverse for a given function? I'm not going to answer that. I want you to contemplate that. So let's go ahead and find the inverse as state the domain and range of the original function and state the domain of the inverse function and graph them both on the same axes. So we know how to graph lines. This is nothing new. I'm going to graph this line, and it has a 5 intercept. 1, 2, 3, 4, 5. Here's where I intercept, and I have a slope of 1. So this is mx plus b, just as a nice refresher about lines. So it has an intercept, a y part of the intercept of 5, and has a slope of 1. Now you can see on my graph, because this is linear, the domain of f is going to be -infinity to infinity, and the range of f is going to be -infinity to infinity because it's a line. So let's go through the process now. Y is equal to x plus 5. That's my first step. I know it's 1-to-1. I can see it's a line. It's a pass horizontal and vertical line test. And then I'm going to have a y minus 5 is equal to x. Then my last step is f inverse of x is equal to x plus minus 5. There is my inverse. This is going to be the range of inverse of f. This is going to be the domain of the inverse of f. Now, this is a graph that has a -5 intercept. So here's my -5 intercept, and here's my line. Here is the line x is equal to y. Not really anything interesting. You can see that the line, the first equation f of x, the second function f inverse of x, and the line y equals x are all running parallel because they have the same slope. So it's really nothing interesting there. Let's take a look at b. Now b is a little bit more interesting. So I have, this time I'm just gonna give you the graph because we're gonna go through rational functions. And so I'm just going to give you the graph of rational functions, or I could think about it in terms of translations maybe, but I'm just going to give you the graph. So I'm going to do first my domain. My domain of f is everything but -3. So I'm going to go with -infinity to -3, union between -3 to infinity. So right out of the gate, I know that this is the range of the inverse. I don't have to do any work. I know that's the range of the inverse. Now the range of the original function, we can do it by looking at the parent or toolkit function, which is the reciprocal function, and do it with transformations. That's one way of doing it. Or we can just think about this logically, because we haven't started graphing rational functions yet. And this is a rational function. It's 2 over x plus 3. And I think about the fact that there's no way my output is ever going to be 0, right? There's no value for x that will make my output equal to 0. So that would tell me that my restriction on my range is 0. So the range of f is going to be negative infinity to 0, union between 0 to infinity. Now this then gives me the domain of f inverse. Now let's find the domain, or let's find its inverse. So the first thing I'm going to do, I'm going to scroll in so I can do with the space down here. So I have y is equal to 2x plus 3. I'm going to multiply both sides by x plus 3, and I get x plus 3 multiplied by y is equal to 2. I'm going to divide by y. So I have x plus 3 is equal to 2 divided by y. X is equal to 2 divided by y plus minus 3. Make it a single fraction, so I have x is equal to 2 minus 3y over y. F inverse, my last step, f inverse of x is equal to 2 minus 3x divided by x. All right. So, and this confirms, right? This confirms that my range is not equal to 0. So if I wasn't able to think about this logically, I can go ahead and find my inverse and see if I have any restrictions on the domain of my inverse function. In this case, I picked up x as being 0, so therefore this confirms, or I can do it this way. So sometimes it's easier to find the inverse function first before we decide what the range is. Now, to graph this function, here's my graph. My restriction on my first one was -3, so at -3 I'm going to have a vertical asymptote. This is where x cannot equal -3. It's my vertical asymptote. And this is just a transformed function of the reciprocal or parent function, so it's going to look something like this. My y-intercept, all I have to do to figure out my y-intercept is put in 0 for x, and I get 2/3, so I guess that actually should come down a little bit further there. So a little bit further, so it looks something more like that. And so here is my original function f of x. Now, this point is a key point. My point, which was the point 0, 2/3, on my inverse becomes 2/3, 0. So it's going to go 2/3, 0. So that is going to go to that point right there as inverses. Because this vertical line is x cannot equal -3, that means on its inverse, it would be y cannot equal -3. So y cannot equal -3. This is a horizontal asymptote, which is y is equal to 0. And then this is the vertical asymptote, which is reciprocal, x is equal to 0. Don't worry if you're like, what? Because we're going to go over this. It's not a big deal. We're going to go over this. Okay, so my inverse function is going to look something like this. It's going to look something like that, and then something like that. So there is my inverse function. And I didn't even need to know much about transformations. All I'm doing is the parent function and finding a y-intercept or x-intercept. So I didn't need to know anything about transformations. I don't need to know anything about rational functions. I'm just taking the parent function, and I know what the parent function should look like, because that's in the very beginning of this chapter. And then I just said, okay, logically, this has to happen. Okay, so here is the function x cubed, -x cubed plus 3. The domain of my original function is everything because it's a cubed function. The range of my original function, I get everything. So I immediately know the domain of my inverse. I immediately know the range of my inverse. So let's go through the process of y is equal to -x cubed plus 2. Subtracting 2 from both sides, y minus 2 is equal to negative x cubed. Multiplying everything by negative 1, I get 2 minus y is equal to x cubed. Taking the cube root, I have the cube root of 2 minus y is equal to x. Last step is f inverse of x is equal to the cube root of 2 minus y, or 2 minus x. And then I just realized, by the way, that I haven't been checking. What? So let me go ahead and finish this graph, and then we're going to go ahead and check it. We're going to check this one. I didn't check them on the other. I was just so excited about graphing them. I just love graphing. So anyways, let's go ahead and graph this. The parent function is the cubed. Even if you don't know transformations, you can do it by point. If you put in 0, 2 comes out. So here is the original 2, 0, 2. That means my inverse must be 2, 0. So I'm doing red as the inverse, black as my original function. If I put in 1, so I can do this totally by ordered pairs without transformations. If I put in the number 1, I get negative 1 out, or positive 1 out. So here is the 0.11. Well, that's also the 0.11 for its inverse. Not very helpful. Let's put in negative 1. So negative 1 cubed is going to be negative 1. The negative 1 out front means it's going to be positive 1 plus 2, which means I'm going to come up here to negative 1, 3. Now, what I was doing is I was just putting negative 1 in right here. That's how I got that answer. So I have positive 3, negative 1. That means doing positive, or negative 1, positive 3 must be positive 3, negative 1. So I'm going to go to positive 3, and I'm going to go down to negative 1. So here's what my original function is going to look like, and here's what my inverse function is going to look like. This is the line y is equal to x. Last one, and then we're going to look at the answer. We're going to do the table, because it's really important to be able to use tables and graphs and algebraically find, oh, darn it, and I said I was going to check. So let's do the checking on this one. Let's do the check. So f composed of f inverse of x is equal to f of, this is what I think my inverse is the cube root of 2 minus y. So this is going to be negative cube root of 2 minus y, quantity cubed, plus 2. This is equal to negative 2 minus y plus 2. And this is going to then give me negative 2 plus y plus 2 is equal to, and that should be x. Man, this all should be x's. Going too fast, thinking about other things, not helpful, so it equals x. Let's take a look at my last composition. So I have f inverse composed of f of x. I need to slow down. And this is going to be f inverse of negative x cubed plus 2. So this is going to be the cube root of 2 minus negative x cubed plus 2. The cube root of 2 minus becomes a plus x cubed minus 2. So this does indeed equal x. So I did find the actual inverse. All right, last one. So my domain for f. I set the value underneath the radical greater than or equal to 0. And I know the largest value is going to be 5. So it's going to go from negative infinity to 5. And that tells me right out of the gate, I have the range of the inverse. So even if I don't know anything else, I can go ahead and start the graphing. I'm going to go around the origin, and obviously I can have negative 3 and negative 2 and negative 1, 0, 1, 2. The highest number I can put in is 5. So if I put in 5, 0 is going to come out. So I'm going to come over here to 5, 0. 1, 2, 3, 4, 5. So here's 5, 0. And then I can continue to put in values for x as long as it stays in the domain. And I'm going to get something that looks like this. So here's my original function. Now you can see from my original function that I have the range being from 0 to infinity, inclusive of 0 going to infinity. This becomes the domain of my inverse. So let's go ahead and find the inverse. Y is equal to the square root of 5 minus x. Squaring both sides, I get y squared is 5 minus x. I'm going to bring or x to the left, y to the right. So I have x is equal to 5 minus y squared. And I have x is equal, well then, hello, paying attention here. I have f inverse of x is equal to 5 minus x squared. Now, you are tempted to say, let's go ahead and just graph this baby, right? Let's do this quadratic and it's upside down and I'm going to do the whole thing. But remember, you have this restricted domain right here. That restricted domain says you don't get to have the entire parabolic shape. You're only going to take part of the parabolic shape, and the part you're going to take is the right-hand side. So its inverse would start up here at 5. 1, 2, 3, 4, 5, and it's going to go down like this. This ordered pair of the original function is 5, 0, and the inverse is 0, 5. So domains become ranges, ranges become domains, and now I just need to check. So don't do the entire parabolic shape because you don't get it. It's a restricted domain. It's only from 0 to infinity. Right here is my restricted domain. This is why I don't get this other side of this parabolic shape for the inverse. Now we're going to just do a quick check. We're going to compose f composed of f inverse of x. So this is going to be the square root of 5 minus, and then I have 5 minus x squared. And you can see this is going to be the square root of 5 minus 5 plus x squared, which does indeed give me x. On the restricted domain, that is true. And then f inverse of f of x. This is going to be, what did I start out with? F. So I'm going to put in 5 minus, and then here I'm going to have the square root of 5 minus x squared, 5 minus x, the quantity squared, my apologies. So this is going to give me 5 minus 5 plus x, which gives me x, and there we have it. So make sure you check, because you'll always know whether or not you have the correct answer, and pay attention to restricted domains, whether you have to restrict the domain right out of the gate, or if you end up shaking out with a restricted domain as the inverse function will have a restricted domain because of the range of the original function. So pay attention to that. Now, let's take a look at this table. How do we read this table? Well, if I want f of 1, I'm just going to go input of 1, output of 0. However, if I have an f inverse of 9, I'm going to go along here until I see the 9 as an output, and the input that produces that 9 was an 8. I'm going to go back to f of 3. So my input is 3, my output is 4. However, if I have an f inverse of 3, I'm going to find 3 in the output, and that means my answer is 7. I must have put 7 in to get 3 out. Every time you are doing inverses, you have the answer. You are trying to find what value is associated with that answer. So let me say that again. When you have the inverse, you have the answer or the range of the original function, right? And you are looking for the x value associated to that in the original function. This is going to be important, especially in pre-calc 2, when I'm asking you what angle produced this answer. I'm going to give you an answer. I'm going to ask you what angle produced this answer. When you have the inverse and you're evaluating the inverse at a number, you're trying to find out what input is associated to that output. You have the output, you're finding the inverse, you're finding the input. Okay, here's an application. A car travels at a constant speed of 50 miles per hour. Ooh, this looks like modeling. Constant's important, 50 miles per hour. So we know that what we're talking about is a slope. because we have a rate here. We have something per hour. We have a rate. So they give us this function. They say, I have the d of t, the distance traveled, is equal to 50 times t. Find the inverse function by expressing the time traveled in terms of the distance traveled. Then we're going to call this d of t, or t of d. So I'm going to have d is equal to, so d is equal to 5t, or 50t. I'm going to divide both sides by 50, and so I've got d divided by 50 is equal to t. So my inverse function, t of d, because that's what they wanted me to write this as, is going to be d divided by 50. So we're asked to find t of 180. T of 180, what is that? Is that the distance traveled, or is that the time? Which am I going to put that in? Well, the way it's wrote is that it says I have the distance, right? I have the distance of 180. How long did it take me? How long will it take me if I am going at 50 miles per hour? So t of 180 is going to be 180 divided by 50. And this is going to tell me how long it's going to take me. So I have 180 divided by 50, which gives me 3.6 hours. 3.6 hours. Now remember, we do want to always write these as a full sentence. It took 3.6 hours to travel 180 miles. And then that's pretty much it. So there it is. Inverse functions, really important in a lot of applications within math beyond this level. So please practice these, come with questions, and let us know how you're doing.